On a recent plane trip, I sat next to a young man who was currently a junior at a small college in Pennsylvania. He was very friendly, eager to tell me about his troubles with a girl who offered him a ride to a tattoo parlor, his coach's tactics for defense, and how little he was learning in college. When he found out that I was a professor or a tutor, he decided to help me out by telling me how he cheats on all his tests. I thanked him for the information, but told him that we don't have tests at St. John's College. He was suddenly very interested. He paused for a moment and then asked how the party scene was. Excellent, I told him. Every Friday night, there's a lecture. Since he was so forthcoming, I decided to ask him what he knew about Galileo. He thought Galileo was the guy who dropped things off the Leaning Tower of Pisa, which is quite possibly true, and that Galileo argued that the sun revolved around the earth. Here he had the right topic, but he had his heliocentrism and geocentrism mixed up. These two facts about Galileo, that he showed that bodies do not fall with speeds proportional to their weights, and that he championed Copernicanism over Ptolemaic astronomy, are probably the two most well-known features of Galileo's corpus. And yet, I'm not sure that juniors, after studying Galileo for a week in junior mathematics and a month in junior laboratory, would have learned either of these things from their study. We don't study why Galileo rejected Aristotle and Ptolemy. We study a new science that Galileo built upon the apparent ruins of Aristotelian natural philosophy and metaphysics. A science of the actualized infinite in the mathematics tutorial, and the study of local motions described in the third and fourth days of Galileo's last published book, The Two New Sciences. The Two New Sciences is a discourse between three friends, Simplicio, Sagredo, and Salviati. On the first 2 days of this 4-day discussion, the three friends discuss a new science concerning the resistance of solid bodies to separation. While there are theorems sprinkled throughout these 2 days, the banter between the friends leads us, for the most part, gently and slowly through the mathematical and physical arguments. Along the way, we are treated with numerous diagrams. Some of them are purely geometric, but many more are intricately drawn sketches of ropes with frayed edges, beams with knots and grains that look like olive, not pine, and crumbling arches of brick that support not only beams, but plants with branching roots that are breaking through, clumps of moss, and new sprigs with veined leaves. On the third and fourth day, readers begin with the unnamed academician's Latin text, rather than a friendly Italian conversation with our three interlocutors. The Latin text describes the locomotion of disembodied movables that are more like mathematical points than the natural bodies in days 1 and 2. The diagrams are reminiscent of Book 5 of Euclid, rather than the drawings of olive beams, braided ropes, and crumbling arches. What we see is an academic mathematician, one who precisely defines equable motion, naturally accelerated motion, and projectile motion, then applies Euclid's theory of proportion and Apollonius's study of conics. The third day, in particular, is remarkably spare. Only 15 of its more than 75 pages are Italian dialogue. The remainder, mathematical theorem after mathematical theorem, all in Latin. It is on the third and fourth day, with this spare Latin text on the mathematics of motion, that our junior laboratory begins. If one ignores nuance, the use of proportion, geometrical corollaries, and blurs one's vision, then one could summarize our readings thus. In 6 theorems on equable motion, Galileo shows that speed is distance divided by time. In the next 6 theorems on naturally accelerated motion, he shows that a distance a body falls is 1/2 its accumulated speed times the time of its fall squared. In the final 2 theorems on projectile motion, Galileo demonstrates that a body can simultaneously move with equable motion in one direction while falling with naturally accelerated motion downward, resulting in a parabolic path. What we study in the third and fourth days is Galileo's last published work, written at the sunset of a life exhausted by a revolutionary study of motion. Published as his body was bedridden by disease, his eyesight failing, his person imprisoned, and his soul shattered from the recent death of his beloved daughter. This monument risks seeming for us an unremarkable dawn, a new beginning we might unconscionably sleep through, a dry academic Latin textbook in which two elementary equations for moving bodies are derived. But the new beginning that we study is the distillation of a lifelong argument between Aristotle and Galileo. Galileo lets us hear echoes of this argument in his dialogues by including the Aristotelian Simplicio among his characters. While Simplicio will argue for the Aristotelian approach tenaciously and with spirit, his understanding is often secondhand, rote, and handicapped by a poor mathematical education, consisting in nothing beyond Book 1 of Euclid. Salviati and Sagredo often team up and ridicule the Aristotelian account and tend to just ignore Simplicio altogether whenever the discussion requires mathematical expertise. It often seems that Galileo is not treating the Aristotelian worldview fairly, as Simplicio himself complains, allowing Salviati to vaunt over an impoverished, dried up, rather rubbish version of Aristotelianism. If Aristotelianism is so ridiculous, why include it at all? Why have Simplicio partake in these dialogues? Galileo's new science of locomotion is now old and familiar to us. Because of this, we might have a hard time seeing Galileo's theory without first becoming strangers to it. One way to do this is to immerse ourselves in another way of thinking about motion. And this is, in fact, what we do in the program by studying Aristotle. By studying Aristotle, we are able not only to see a cohesive, beautiful, and philosophically rich way of understanding motion, we are also put in a better position to see how our own understanding of nature is itself a theory that requires attention and thought. I think that Galileo put Simplicio into the dialogues so that we notice that Galileo's steps were not taken out of necessity, by habit, or from authority, but consciously taken to set himself upon a new path to understand nature. Simplicio is there so that we notice that Galileo isn't simply doing mathematics, he is also philosophizing. Simplicio is there to remind us that Aristotelian philosophy was more than any part that Galileo might contradict. It was a whole philosophy of nature, and that this, quote, new way of philosophizing tends to subvert all natural philosophy and to disorder and set in confusion heaven and earth and the whole universe, end quote. Simplicio is in the dialogues because Galileo is still trying to understand the significance of his disagreement with Aristotle. So what is this Aristotelian natural philosophy that Galileo threatens to subvert, disorder, and set in confusion? There are countless small, derisive references to the peripatetic philosophy throughout both the two chief world systems and the two new sciences. Simplicio championing it and defending it in turn. But tonight, I thought it would be worthwhile to turn to an earlier text in Galileo's career, On Motion, or in Latin, de motu. And I use the Latin just because it's hard to say on motion repeatedly, so in de motu is easier. Galileo wrote and rewrote de motu while he had a chair in mathematics at the University of Pisa at the outset of his career, around 1590. Some hypothesize that de motu was written in preparation for lectures on Aristotle, others that it was written for publication, although it was never published. Perhaps it was both. As a young professor, he is more conservative than when he is older. He works from a foundation established by Aristotle's natural philosophy. Galileo reminds us of Simplicio in these lectures, adhering to an Aristotelian theory without fully understanding its consequences. Here we encounter Galileo wrestling with Aristotle rather than pumping his fist in triumph. Although he eagerly points out inconsistencies with the same iconoclastic spirit we see in the later dialogues, the apparent goal is not to refute, but to improve upon Aristotle by supplementing his account with mathematical reasoning inspired by Archimedes' writings on the balance, making Aristotle's theory more consistent with our experiences of moving bodies, or that's the goal anyways. As Galileo develops the consequences of these changes, we'll see a description of nature emerge that is at odds with the foundation, Aristotle's definition of nature. Okay. Aristotle's theory of natural motion. I'll begin with a few basic ideas from Aristotle's natural philosophy before giving a more detailed account of what we might call Aristotle's science of the locomotion of bodies. I hope that most of you can say what Aristotle's definition of nature is. Maybe not as readily as Simplicio, but hopefully it's in there. But just in case. Aristotle defines nature in the beginning of the second book of the Physics. Quote, "Nature is a principle of cause, or of being moved, and of being at rest, in that to which it belongs primarily, in virtue of itself, and not accidentally. Nature is not deer, trees, rivers, and soil, but the cause of motion and rest in deer, trees, river, and soil. The cause that belongs to these things in virtue of what they are and not accidentally. Nature is the reason something moves or something rests when it moves or rests because of itself. Nature is an internal cause of motion or rest." I've repeated this multiple times in different ways. So as it comes up in the lecture, you should recognize it. Nature is not the only cause of motion. Another cause that we are familiar with is force or violence. If I lift a stone or a pen, it does not move because of its nature, but because of a force which I apply to it. All local motions will have a cause, either a natural cause, which is internal and belongs to the body, or a violent cause, which is usually external and is the result of a force being imposed upon the body. For Aristotle, natural motions are eminently more interesting than forced motions. So he'll occasionally talk about forced motions, but most of the time he's interested in the natural ones. Now, when we turn to study nature, the internal cause of motion and rest, we are faced with two kinds of things. There are things that have life or soul, and things without life or soul. In the Physics, Aristotle says that having an internal source of motion and rest is a characteristic of life and peculiar to living things. But for Aristotle, there's an intriguing puzzle about the motion of non-living things. Why and how do they move themselves without a soul? So, pen doesn't have a soul, but it clearly moved. Why and how? Now, when we turn to study nature, the internal cause of motion and rest, did I already read that? Yes, I already read that. So Aristotle's account of nature needs to stretch to incorporate a kind of motion that originates in a thing without originating in a thing's soul. In this lecture, we will call the natural motion and rest of a non-living thing the natural motion and rest of a body. Aristotle will say two things about a body's motion, and there's some tension between these two claims, which we'll need to address. First, a body's source of motion, a body's nature, is the heavy and the light in the body. In De Caelo, Aristotle will say that bodies have, quote, in themselves some spark, as it were, of movement, end quote. This spark is the heavy and the light. If we were to form an analogy, we could say that soul is to an animal or a plant's natural motion as spark is to a body's natural motion. But the second claim that Aristotle makes is that the body does not move itself as an agent. This motion is pure passivity. Here is Aristotle in the Physics, quote, in all these cases, the thing does not move itself, but it contains within itself the source of motion, not of moving something or of causing motion, but of suffering it. Here we have Aristotle pushing against the idea that we should understand the heavy and the light as anything analogous to soul. The body's motion is pure passivity. The spark is not a soul, but a passive potential for a kind of activity, being at rest in a particular place. The idea here is twofold. First, while a stone resting on the ground will never move itself, if I lift that stone up and release it, the stone will move. So the spark does not turn into a roaring fire by itself, but only when one uses bellows to fan the flame. Second, the heavy and the light do not choose their place of rest and where they will move when they do move. There is no internal account for why they move where they move. Aristotle says that ultimately, quote, these things are moved by that which brought the thing into existence, and made into existence and made it light and heavy. We can now turn from these few basic ideas underlying Aristotle's natural philosophy to some more specific claims in his account of how the heavy and the light can be used to describe the natural motions of bodies. First, and of primary interest tonight, is this. Aristotle believes that bodies fall with speeds in proportion to their heaviness and lightness. In the Decalo, Aristotle gives the following example. So this is illustrated in the handout labeled Figure 1. It's kind of cut off at the top there. If we have a body B that falls through the whole of CE in a given time, and then we divide both the body and the line in the same ratio, then the part of the body that we've cut off will complete that part of the line in the same time as the whole body moved through the whole line. Kind of make sense? So it's like you have the whole body, it's going to fall, let's say in a second, you take that, a part of it, some part of it, and take that same part of the line, and now that part of the body, in a second, will just fall that part of the line. So it's going to slow down dramatically, that little part will slow down. This means that a stone twice as big as another stone, that is with twice the heaviness, will fall twice as fast. Aristotle will give similar examples for the light as well as the heavy. A fire twice as large as another fire will rise twice as fast. Paired with this claim is a claim about how bodies fall through different mediums. If one is given a body, it will fall with a speed that is inversely proportional to the density of the medium. If water is twice the density of air, then a body will fall half as fast in water as it will in air. And yeah, the word for density is a little bit weird. It's not the same as our density, but sort of like bodily thickness or something like that. Aristotle also gives an explanation for how and why bodies naturally accelerate. In Decalo, Aristotle says that when a body naturally falls downward or rises upward, it moves towards fulfillment and, quote, comes into that place, quantity, and quality which belongs to its form, end quote. The idea that something moving upwards would change not only in location, but in quantity and quality might seem strange. So again, like as a rock is falling, it doesn't just change its place, but the rock itself is somehow changing as it falls. We might remind ourselves that for Aristotle, motion is not simply locomotion. Motion is a general category. It is a becoming. It's an actualization of a potentiality as such. The heavy doesn't just move downward. It has a place in the cosmos, the center. When the heavy is in its place, it is fulfilling its purpose. It is at work being itself. It is actualized. Similarly with the light. When the heavy moves downward, it is not simply changing its place. It is becoming more itself. It's like becoming more comfortable. It is, to return to the quote above, coming, quote, into that place, quantity, and quality, which belongs to its form. This means that as the heavy moves downward, it gets heavier. And because it is heavier as it falls, it actually moves faster. Galileo adds in the margins Thomas Aquinas' way of putting this, quote, Aristotle held that the speed of motion is increased because the weight of the body is more concentrated and strengthened as the body approaches its proper place, end quote. So we now have the basic outlines of Aristotle's account of nature insofar as it concerns the motion of bodies and how he uses this to explain the natural motion of bodies. Where a body is at rest, where it moves when it is displaced, the speed with which it moves, and why a body accelerates. But because the heavy and the light are not soul, they are not active principles, but passive principles, we can still ask the question, why does the light go up and the heavy down? To answer this question, Aristotle says that we have to look outside the bodies to, quote, that which brought the thing into existence and made it light and heavy. Okay, part 2. This is Galileo's critique of Aristotle. Galileo thinks that Aristotle was wrong, that speed is proportional to weight. Galileo prepares many thought experiments which might not refute Aristotle, but they work on the reader's imagination so that Aristotle's claims become more problematic. Because Galileo writes these thought experiments to persuade, I'll focus on the one that I found most persuasive and try to explain why I found it so. Galileo instructs us to imagine two bodies of equal weight falling next to each other with equal speeds. Just falling. As these bodies fall, they are shoulder to shoulder, and then at some point, they become attached. An Aristotelian will be compelled to say that once they become attached, they will go twice as fast, just suddenly go twice as fast. Galileo concludes that it is obvious that this is not the case for anyone who, quote, looks at the matter simply and naturally. And he gives us, unfortunately, no help on this. He is trying to turn this essay into a dialogue, but he never completes it. So I would love to read that. As we consider the example, in an attempt to look at the matter simply and naturally, we might notice that the sudden increase in speed is coincidental with the cohesion of the two bodies. The cause of the increased speed doesn't seem to be more weight exactly, but the fact that a given weight that was in two bodies is now suddenly in one body. Why should that matter? How would this cohesion increase the speed? Surely the bodies will continue going the speed that they had been going, whether the bodies are rubbing shoulder to shoulder or holding hands, so to speak. Now, is a chunk of wood any different from two halves of wood, sort of holding hands, joined together? I don't see why it would be. So it must be that the larger chunk of wood falls just as fast as any of its parts would fall, and it just so happens that all these parts are sort of holding hands. Now, perhaps this is not what Galileo meant by looking at the matter simply and naturally, but I am sure that it is just this sort of inner dialogue that he wants his readers to have as he goes through his thought experiments. There is no indication in these lectures that Galileo rejected Aristotle's claims based on a field trip to the Leaning Bell Tower in Pisa. If anything, the sort of examples he gives indicate an approach that puts more weight on reason and imagination than any particular experience. The example we have just given of two bodies being joined together mid-fall is just such an instance. How could bodies be made to do this? A few pages back, Galileo gives another counterexample to Aristotle's claim that speed is proportional to heaviness. Here, he asks us to imagine two lead balls, one 100 times as large as the other, both being dropped from the moon. In both cases, the examples are not the sort of thing one can put to an actual test. Despite what one will hear about Galileo being among the first experimentalists, it's clear in de motu that his theories were not based on results from experiments. Rather than torturing nature for answers, he was more likely to interrogate his imagination and think through a problem theoretically. Galileo says that he likes to, quote, employ reasoning at all times rather than examples, for what we seek are the causes of effects, and these causes are not given to us by experience. The ability to guide his own imagination and reason until he sees a clear relation of cause and effect is one of Galileo's greatest points of pride. In both the two new sciences and the two chief world systems, Sagredo will repeatedly compliment Salviati on his ability to do just this. Descartes, when he first reads the two new sciences, is just appalled by this. He's like, who writes something where they like compliment themselves inside the book? Anyways, okay. Here, for example, is Sagredo responding to Salviati in our readings from the junior laboratory. Sagredo. Too evident and too easy is this reasoning with which you make hidden conclusions manifest. This great facility renders the conclusions less prized than when they were under seeming contradiction. I think that people might generally little esteem ideas gained with so little trouble in comparison with those over which long and unresolvable altercations are waged. This praise, which Sagredo heaps on Salviati and Galileo seems to be heaping on himself, echoes the praise that Plutarch gives to Archimedes. Here is Plutarch, quote, "It is not possible to find in all geometry more difficult and intricate questions, or more simple and lucid explanations. No amount of investigation of yours would succeed in attaining the proof, and yet, once seen, you immediately believe you would have discovered it. By so smooth and so rapid a path, he leads to the conclusions required." Okay, part 3, Galileo's theory of motion. One goal for Galileo is to improve upon Aristotle's account of the speeds of falling bodies. Galileo is willing to reject the claim that speed is proportionate to weight, but he is not willing to reject the claim that there is some relationship between speed and weight. His stubbornness might be difficult for us to understand. Doesn't he see that the speed of falling bodies has nothing at all to do with the quantity of matter? Absolutely not. And this fact, this amazing fact, is what makes me just love Galileo and Motu. At this moment, he is Simplicio. At this moment, he is a dyed-in-the-wool Aristotelian. He believes that nature is a cause of rest and motion in a body. He believes that for bodies without soul, the nature of the body is its weight. He believes that weight just has to be the cause of rest and of motion. But Galileo recognizes that there are some areas of weakness in Aristotle's account. In particular, Galileo will need to finesse the relationship between speed and weight. It can't just be direct proportionality. Galileo has a way to do this. At the age of 22, about 5 years before he writes De Motu, in 1586, he writes a small little essay. It's kind of a lab report, if you will. The topic of his essay, How Archimedes Discovered the Theft of Hero's Crown. He thinks that the method ascribed to Archimedes by others is a, quote, crude thing, far from scientific precision, and not befitting the divine Archimedes. In the remainder of his essay, he argues that Archimedes does not find out the fraud by immersing equal weights of gold and silver in water and measuring the different quantities of spilled water. This would just be really imprecise. He's just like the bathtub story, maybe you've heard that, just water splashing everywhere. That's not scientific. The key is that Archimedes recognized that, quote, solid bodies that sink in water weigh in water so much less than in air, as is the weight in air of a volume of water equal to that of the body. I'll just read that again, it's hard. Solid bodies that sink in water weigh in water so much less than in air, as is the weight in air of a volume of water equal to that of the body. So maybe try one more time in my own words. The body will weigh less in water by exactly the weight of the water that the body displaces. This difference in weight then serves as an accurate measure of the volume of the body, allowing one to precisely measure the differences in the quality or density of two submerged metals that are of equal weight in air. So this allows him to detect the fraud. What Galileo takes away from Archimedes and wishes to apply to Aristotle is this idea. It isn't weight, but essential weight or density that distinguishes bodies from one another. Sometimes this is translated as specific weight, like the weight of the species. Just as Archimedes is able to distinguish gold and silver by their essential weights, Galileo is now able to distinguish all kinds of natures from one another by considering their essential weights. And this, a body's essential weight, this must determine its speed of fall. This is a thrill for Galileo. He's figured out what nature is. He has found the key to determining the speed of any given body. The peripatetics, if they aren't too stubborn, too tied to every last word of Aristotle, are going to love it. He might even get promoted. to philosopher. He's a lowly mathematician, it's considered a very low post, and he really wants to be a philosopher, which means that he needs to be able to explain his Aristotle or improve upon Aristotle. After all, and this is a common saying of the time, quote, "Ignorance of motion is ignorance of nature." He has found the key to motion, the real nature, the essential weight of a body. But to get this theory off the ground, he has to revisit Aristotle's natural philosophy. Can Aristotle's heavy and light be replaced with essential weight? Can motion be explained by the outcome of a balance? Galileo begins confidently, not only sure that he can replace Aristotle's heavy and light with essential weight in order to explain motion, but sure that doing so will improve Aristotle's account of nature in other ways. As we saw above, Aristotle faced a puzzle in explaining the motion of non-living bodies. He was committed to explaining their motion by finding an internal cause, but because these bodies do not have soul or life, they couldn't be agents of this motion. In one way, then, the heavy and the light explain the rest and motion of bodies, but in another way, Aristotle ends up needing to look for a principle outside the bodies to explain the principle of rest and motion. So this is problematic for him. Galileo's way of describing the situation is that Aristotle finally did not have an explanation for why the heavy goes down or the light goes up, but instead was forced to make nature operate, quote, according to chance and whim, unquote. Galileo says that he, quote, anxiously sought from time to think of some cause, if not necessary, at least reasonable and useful, end quote, to determine why the heavy goes down and the light up. Here, too, the key was replacing the idea of heaviness and lightness with essential weight. In doing so, he realizes that nature might have chosen to put the densest at the center and the rarest at the perimeter with, quote, complete justice and consummate wisdom. In doing so, nature has distributed matter equally around the center of the cosmos. The smallest sphere, which is closest to the center, has equal matter, but a lot less space than the larger spheres away from the center. Therefore, the smallest sphere must be the place of substances whose form causes the matter to be compressed in a very narrow space, while those spheres farther from the center must be the place for substances whose form causes matter to expand in ample space. Galileo's account has supplied a formal cause for the cosmos that explains why the heavy, the dense, rests at the center, and the light, the expansive, rests away from the center. Once Galileo suggests that this principle of equality is at work in the organization and the creation of the cosmos, it's natural that he should think it is at work in the preservation and the restoration of the order in the cosmos. In other words, this same principle might be at work not only when bodies are at rest in a perfectly ordered world, but after bodies are disturbed and are working to restore that order. For example, this principle is at work when, after I lift a rock and remove it from its place, I release it and it rushes downwards. For the restoration and preservation of order, nature needs more than a cosmos that was created with matter equally distributed about the center. Nature will need a way to measure inequalities and restore equality. So nature is going to need a balance. Here, Galileo. It is therefore clear that the motion of bodies moving naturally can be suitably reduced to the motions of weight in a balance. Now, in general, a balance measures the relative weights of two bodies. But when Archimedes submerged the scale in water, he was able to determine essential weights. So Galileo hypothesizes that to get an accurate measure of the nature that determines speed, the balance will need to determine essential weight. One arm of the balance might carry the body, but the other needs to take into account the medium. Here, Galileo. The body moving naturally plays the role of one weight in the balance, and a volume of the medium equal to the volume of the moving body represents the other weight in the balance. Just as the crown submerged in water was lifted by the water to the extent that a weight equal to the weight of the water it displaced would lift it, so too Galileo imagines that any medium will lift a body to the extent that a weight equal to the weight of the volume of the medium it displaces would lift it. So this right here, it's sort of resting downwards a little bit, but at the same time, he's imagining that there's a little push upward. And that push upward is equal to the weight of, a little chunk of the air that's equal to this. So it's lightened a little bit, just like the crown in the water would be lightened. Bodies don't fall. So Aristotle thinks that bodies fall with speeds that are proportional to their weight. Galileo responds, bodies don't fall with speeds proportional to their weights, but speeds proportional to this adjusted weight, their own weight less the weight of an equal volume of the medium. Now, as it turns out, Galileo's theory is just as bad as Aristotle's. Galileo seems to recognize this fairly quickly. It's probably why he never published this. Here he is working through an example. This also might be a little hard. So if there are two bodies equal in volume but unequal in weight, the weight of one of them being 8 and of the other 6, and if the weight of a volume of the medium equal to the volume of either body is 4, then we're going to subtract this 4 from the body of 8 and the body of 6. The speed of the first body will be 4, so that's the 8 minus 4, and the speed of the second body, which weighed 6, is now going to be 2. These speeds will now have a ratio, the speeds of the bodies will now have a ratio of 4 to 2, which is not the same as the ratio between their weights, which was 8 to 6. In this particular example, the medium has an essential weight that is fairly comparable to the essential weights of the bodies. So we had a body of 8, a body of 6, and the medium was a weight of 4. The ratio of the speeds in the medium is thus larger than the ratio of the original essential weights. In fact, we see that the ratio in speed could get really large if we find a medium that has an essential weight close to the smaller body, the one of size 6. In this case, one body would drop with some speed, while the other body would not move at all, it would just float. So now that the ratio of the speeds, even if this is just moving very slowly, the ratio of the speeds ends up being infinite. This result actually looks pretty good. Here, Galileo's theory seems to explain why the ratios of the speeds of bodies falling in water seems to be larger than the ratio that the bodies have when falling in air. On the other hand, as the medium gets thinner, as its essential weight becomes negligible compared to the essential weights of the bodies, the ratios of the essential weights should be approximately proportional to the ratios of the speeds. So in very light mediums, Aristotle's claim that speeds are proportional to weights is analogous to Galileo's. Speeds would become close to proportional to their essential weights. So here it would just be like, just look at the essential weight. You wouldn't be subtracting a weight of the medium. The medium is so light. In other words, if we take equal-sized balls of wood and iron, and we drop both of these from a large tower, they should fall with speeds proportional to their essential weights. I won't have anyone up there do that. But, here, Galileo. But note, a great difficulty arises at this point because those ratios will not be observable by one who makes the experiment. For if one takes two different bodies which have such properties that the first should fall twice as fast as the second, and if one then lets them fall from the tower, the first one will not reach the ground appreciably faster or twice as fast. End quote. While it might not have been Galileo's first inclination to head to the tower, it seems like he was not opposed to making a test of his theory once it was in hand. In doing so, he must have been quite disappointed. But he is not yet able to give up the theory. He concludes in the same way that Aristotle would have, quote, "This is not the place to consider how these contradictory and, so to speak, unnatural accidents come about, for they are accidental." It sounds like lab reports, right? Like all these accidental factors. We won't go into them, but surely they account for things. Okay. Let's take a step back from the details of Galileo's theory for a moment. What Aristotle and Galileo seek to explain is how the body's weight can explain its place of rest and its motion. They are looking for an internal cause of rest and motion. Aristotle explains this by turning to the spark inside the body, which determines its place and makes it passively suffer the motion determined for it. Galileo explains place by looking at density and supposing a formal cause in the organization of the cosmos, the equal. Galileo explains motion by having us imagine how a balance tips when bodies of unequal essential weights are placed on its arms. Galileo has asked us to supplement the internal principle of motion and rest, the body's essential weight, with two additional principles, a principle of equality and the principle of the balance. But what is the principle of the balance? What is it that makes it move? Does the balance have a nature? Certainly not, says Aristotle. But the balance does have some sort of laws governing it. This is not just a law of equality. The balance is not an equation merely telling us that two quantities are equal. The balance is dynamic. It is telling us something about forces. Galileo puts it this way, quote, "A heavy body tends to move downward with as much force as it is necessary to lift it up. On each side of the balance, a body pushes down, but on each side, a body is also being pushed upwards. The principle of the balance is that every downward force is transformed into an equal and upward force. Balances work because they pair these opposing forces. Galileo seems to think that this principle of the balance is not just present in a balance, but is present everywhere and always. In addition to the internal principle of rest and motion, the body's essential weight, Galileo has introduced these two additional principles. Neither of these principles belongs inside a body. Both are principles about how one body relates to another body. In fact, the principle of the balance is best understood as a principle about opposition between bodies, about the forces that bodies exert upon one another. It's about violence. This is a problem for an Aristotelian. A natural motion is being given a very unnatural explanation. Galileo acknowledges the difficulty himself. It is therefore clear that this kind of motion may be called forced, although commonly called natural. Galileo does not flinch. I think he should, but he doesn't. In what follows, there is no apology and no explanation for this radical departure. By introducing a formal cause, the equal, by explaining motion and speed with the balance, Galileo has not improved the Aristotelian account. He has actually undermined it. Natural motion has gone from being internal to the body to being caused by a relation between one body and another body. Motions, which were once the actualization of the potentiality of a single body, are now understood to be violent outcomes of a contest of forces between bodies. Galileo has shown himself to be a wolf in sheep's clothes. The principle of equality and the principle of the balance are not compatible with Aristotle's definition of nature. Archimedes might move the science of motion forward, but the science won't be compatible with Aristotle's natural philosophy. Nature is no longer the principle of motion or rest within a body. Nature has been replaced by a balance, a contest between quantities of matter. Okay, now for the tricky part of the lecture. Inclined planes. Despite his failure to let me get some water. Despite his failure to explain the speeds of falling bodies, Galileo charges onward. He now wants to use the principle of equality and of the balance to solve a problem. How fast do bodies fall along inclined planes? And below, I'm going to quote a larger passage. It's not particularly remarkable, apart from his palpable excitement and, not unrelatedly, how many times he uses the word problem. Here's Galileo. The problem we are now going to discuss has not been taken up by any philosophers, so far as I know. Yet, since it has to do with motion, it seems to be a necessary subject for examination. And it is a problem no less necessary than neat and elegant. The problem is why the same heavy body, moving downward in natural motion over various planes, inclined to the plane of the horizon, moves more readily and swiftly on those planes that make angles nearer a right angle with the horizon. And in addition, the problem calls for the ratio of the speeds of the motions that take place at the various inclinations. The solution of this problem, when first I had tried to investigate it, seemed to require explanations that were by no means simple. But while I was examining it more carefully and was trying to analyze its solution into its basic principles, I finally discovered that the solution for this problem, as of others which at first glance seem very difficult, depended on known and obvious principles of nature. I guess probably can guess now the principle of nature will be the balance. I'm just going to quickly go over here. The basic idea is he wants to know the ratios of speeds of a body falling down different inclines. So if I were to make this body go down the incline right now, it might seem to go fairly slowly. But if I increase the incline, it's going to go faster. Or seem to go faster. And if I crank it up all the way and just drop it, essentially rotate, it's going to go very fast. So he's interested in finding the ratios of these speeds. In past junior laboratory classes, I have sometimes wondered whether we are studying nature, machines, nature as a machine, or machines as if they were nature. This passage led me to have a new way of thinking about this question. With Galileo, the subject matter seems to be shifting. The balance stands midway between nature and machines. It's not unnatural. For Galileo, it even reveals nature. In fact, it has become the principle of motion and of rest. But the balance with intelligent use very quickly becomes a lever. It becomes a machine. The balance brings together nature and machines, allowing us to create problems that are no longer simply mechanical problems for artisans in the shipyard, but problems that are now demonstrations of how nature works. The instruments of the shipyard are no longer for the artisans alone. They are now the instruments the philosophers and the mathematicians will need to use in the laboratory to reveal how nature works. Galileo moves from understanding nature as an individual principle inside a body to thinking about nature as a beautiful, intricate tapestry of problems, infinite interconnected balances, each in delicate equilibrium, systems of equations joined by the weights, speeds, and forces of individual bodies. Here we only see the introduction of a single problem, but the excitement, the repetition, makes me think that Galileo is no longer seeing individual natural bodies. He is seeing a web of bodies connected and revealed by the balance, an infinite and infinitely intricate machine, giving rise to the promise of problems everywhere. But right now, we only have a single problem. How fast will a body go down planes of different inclinations? The known and obvious principle of nature, which will play an essential role in his solution, the balance. Galileo will show how he can weigh the body on different tracks and thus predict how fast the body will go. So again, he's still convinced that the weight has something to do with the speed. So if he can figure out how to weigh the body when it's on tracks of different inclination, then he's going to know how fast the body's going to move. It takes a bit of geometry, a few diagrams, and maybe some gestures towards our laboratory equipment to see how Galileo imagines the balance at work in his study of inclined planes. So in the handout, you'll see an enlargement of Galileo's diagram. This is figure 2. This part's kind of tricky. I hope it's okay. So the circle represents two things. First, it represents a circular track on which a body could fall on its concave surface from D to B. So here we have the circle. I have a track. It only goes 90 degrees because that's all that we need, but you can imagine sort of a track going all around the circle. Second, the circle also represents a balance, like the Newton's wheels that we study in freshman laboratory. The axle of the wheel, the fulcrum of the balance, is at A. So in the diagram, that you can see that wheel, right? So it's both the track and it's what we call a Newton's wheel. We really should call it Galileo's wheel, but Galileo's wheel. We are to imagine two things happening in tandem. A body is falling down the circular track from D to B, and at each moment we could pause it and ask, what is the weight of the body at that point? What is the weight of the body that we could put on the opposite side at C that would balance the falling body at that moment? So again, try to gesture here a little bit. So I have this body, and it has a weight right here. We can suppose that it might balance the weight do you guys see the gold weight over there? It might balance that gold weight right now. But as it falls along the track, it might need less and less weight to balance it. Right, so at the very bottom, how much weight would it require? None. Right? We need no weight to balance it. But as it goes down this path, it's going to need less. The problem Galileo is investigating concerns the planes that are going to be tangent to the circular track, the planes that are inclined to the horizon. We only have I only have two such planes drawn. But obviously, so I have the vertical one, and then I have one just at an angle. But obviously, there are an infinite number of these planes that could have been drawn. Galileo, as we saw above, is interested in this problem: to find the ratio of the speeds of the motion that take place at the various inclinations of the planes inclined to the horizon. For example, he is interested in finding the ratio of the speeds of the body falling down the vertical plane, EF, to the sharply inclined plane, GH. Galileo reiterates the principles of the balance here. A heavy body tends to move downward with as much force as it is necessary to lift it up. So the ball is going to tend downward with exactly that force that it would be necessary to lift it up from the opposite side of the wheel. Weight, as measured by a balance, will allow us to see how much force is necessary to lift a body up, and thus measures the force of a body's tendency downward and its speed. The circular balance is there to determine how the weight of the body varies with the different inclinations of the planes, so that we can determine the speeds along any inclined plane. The balance will give us the solution to our problem. At point D, furthest away from the center of the circle towards the right, the tangent of the circle is vertical. The track does not lighten the weight of the body at all. The weight needed at C to balance the body at D is going to be equal to D's weight. Does that make sense? Yeah. As we travel down the circumference, we come to point S. At point S, Galileo suggests that the body is not as heavy as it was at point D. The body has been lightened by the ramp. He actually has a theory of impressed forces here. So the ramp is sort of impressing a force on it. It's lightening the body. I won't talk about this too much tonight, but he basically thinks it's like making it hotter, a little bit airy, gives it a little bit more lift. So it's not Newtonian at all. With weight, what weight at C would be necessary to balance a weight at S? Galileo believes that we can set aside circular ramps in the inclined planes and now simply consider the balance. The body has moved from D to S on Newton's wheel. As we know from freshman lab, we'll need to draw a perpendicular from S up to the line CD to determine the horizontal distance of the body from the fulcrum. This distance will end up being AP, which is less than the previous distance, AD. Because the body at S is now closer to the fulcrum, we will need a smaller weight to balance it at C. The ratio of the new smaller weight to the previous weight is AP to AD. Galileo concludes that the ratio of these weights is the ratio of the downward tendencies of the body, and so the ratio of the speeds along these two planes. So the speed along EF is going to be to the speed along the plane GH, as AD is to AP. The inference that Galileo makes, that the weight the body has on the balance at a point is the same weight that the body would have on the track with an inclined tangent to that point, remains unexamined and unexplained. While the circular balance is very much present in this diagram, the balance is not present when we have a simple inclined plane. There's no balance there. And yet, Galileo seems to think that there is. Every time a body falls, we could explain the speed of its fall by recognizing that a balance is at work. The weight that would be necessary to balance this body is the force with which the body tends downward and therefore proportional to the speed with which the body will fall. While the balance isn't visible, the principle of the balance is everywhere at work. The balance is woven into the relations that exist between all bodies. For me, the pattern still floats above the fabric of nature. It is clearly meant to be woven in, but how and why the balance is attaching itself to the ramp, to the body, to the medium, remains murky. What I would like to know, is why it is that the balance should succeed in measuring how these ramps lighten the weight. Perhaps there's some clue in what follows. Galileo continues his exposition with what appears to be a superfluous explanation that directs our attention outside the circle, towards a triangle that is geometrically similar to the ones that are inside the circle. So back to the diagram again. So you might see triangle APS and compare it to the triangle SPQ, which sort of juts out. About this, Galileo notes that as DA is to PA, so is QS to PS, i.e. the length of the oblique descent to the length of the vertical drop. That is, the ratio DA to PA, which stood in for the ratio of the weights necessary to balance our body on the vertical and oblique incline GH, have the same ratio as QS to SP. When we take two inclined planes of the same height, or a drop and an inclined plane of the same height, it turns out that we'll get this very ratio that we had when we looked inside the balance. With his analysis of the exterior triangle, Galileo directs our attention away from the balance and towards the ratio of the paths which two bodies will take when they are released from the same height, but along different inclines. He says that the speed of fall is inversely as the lengths of the planes. Here, the ratio of speed is not derived from the heaviness of the body, but has something to do with the height from which the body falls and the lengths of the planes having those equal heights. Galileo has given us not one, but two ways to see how this same ratio emerges from the diagram. Because of this, he also seems to be suggesting two different explanations, one based on the body's weight, the other on the body's height and the path it takes. Which account of the ratio would give us a better explanation for the difference in the speed of the body? Or do these two explanations have some relation to one another? Galileo started the essay believing that weight caused speed, but his analysis here seems to hint at a new opening to explaining speed in other ways. Perhaps something having to do with the height from which a body falls and the path that it takes. Perhaps he thinks there is a way in which something associated with speed is causing weight. Galileo does not help us. He leaves these two expositions, these two similar triangles, these two equal ratios, side by side. This juxtaposition of two mathematically equivalent ratios might remind us of the third chapter of the third book of Ptolemy's Almagest, where Ptolemy gives the reader two hypotheses that result in identical phenomena. Just as Ptolemy gives us mathematically equivalent eccentric and epicyclic diagrams of the motion and of the heavenly bodies, Galileo gives us mathematically similar triangles, one made from the distances to a fulcrum, the other by the paths of the moving bodies. Galileo's first triangle suggests that the speed down more sharply inclined planes can be explained by greater weight. The second triangle suggests that the speed down inclined planes can be explained by considering the height from which the body falls. Ptolemy's circles and Galileo's triangles could be carving at the joints of nature, but they also could be mathematical tools, seductive geometric figures that invite us to imagine physical structures that may or may not be there. After giving his account, Galileo is eager to share all manners of problems that can be solved with his method. He just starts listing them. The one he culminates his discussion with is this. Given two bodies of different essential weights, which fall at different speeds, how to construct a ramp so that the faster body falling down the ramp will fall in the same time as the slower body in free fall. For example, presuming that the steel ball will fall faster than the wooden ball, Galileo would like to construct a ramp for the steel ball so that it will roll down the inclined plane in the same time that it would take the wooden ball to fall freely. Here he seems eager to use the inclination of ramps to balance speeds, in the same way that a balance uses the distance from a fulcrum to balance weights. Ptolemy was incredibly successful in saving the appearances. He used the circle to effectively predict where heavenly bodies would be and when they would arrive. Galileo finds that he is much less successful in saving the appearances. But he doesn't acknowledge any doubt in his theory. Instead, again, he uses the same excuse we saw above, accidental factors. The problems that Galileo solves are constructions, but merely mental constructions. When these constructions are realized in the world, he does not despair when the consequences he has derived are not seen to be true. Unlike Ptolemy, Galileo is not yet able to save the appearances. Okay, conclusion. Galileo might have been wrong that essential weight is the cause of motion and rest in bodies. But in developing this idea, he introduced two principles inspired by his study of Archimedes, the principle of the equal and the principle of the balance. Both are enormously influential in the subsequent study of physics. Neither of these principles resides in bodies. They are instead principles that govern the relations between bodies. They are principles equally at home in political philosophy as natural philosophy. We can see this in Galileo's language. He appeals to equality, prudence, justice, and harmony in his explanation for the natural place and position of rest for bodies. Galileo then appeals to the balance, a symbol we use for the weighing of injustices, in his explanation of motion. These principles from Archimedes that Galileo introduces to his study of nature are not internal principles of motion. They are not compatible with an Aristotelian account of nature. When Galileo turns to study astronomy, he will not begin by trying to improve upon Aristotle's account. Instead, he starts all over from the beginning. The source of motion is not where you think it is. This radical departure from Aristotle becomes his beginning point. It is as if Galileo once fell for an enormous cosmic prank and is willing to risk imprisonment to prove to the cosmos that he won't fall for it again. He once thought that the principle of motion is in the thing that appears to move, but now when he sees the sun rise and set and the stars revolve around his head, he knows better than to think the principle of motion is in those bodies. In Jacob Klein's essay on modern rationalism, he says the following, quote, "Mathematical physics is the most important part of our entire civilization and actual life. The principles of mathematical physics are basic to our whole way of thinking and behavior." At the conclusion of the essay, he points to the vast machinery of our society and the indirectness of our contact with the world. Direct contact replaced by a symbolic unreality. This was before iPhones. I just can't imagine what he would have said. Klein claims that, quote, our work, our pleasures, even our love and our hatred are dominated by these all-pervading forces which are beyond our control. These are radical claims. After rereading Klein's essay this fall, I had the opportunity to talk with Ms. Brand, a longtime friend of Klein's. I finally got up the courage to ask her, was Klein exaggerating? Did he really think that mathematical physics is the most important part of our entire civilization and actual life? That our work, pleasure, love, and hatred are dominated by these all-pervading forces? Her answer, oh yeah. Well, oh yes. After studying de motu and watching Galileo struggle to reconcile Aristotle's philosophy of nature with Archimedes' mathematics, I'm less incredulous of Klein's claim. The movement that I see in Galileo's early study of natural motion, the move away from thinking about nature as a principle of rest and motion in individual bodies, towards thinking about nature as a contest between bodies, and eventually thinking of all motion as the consequence of forces that originate entirely outside oneself, that is quite familiar. The way we love and hate, the way we think about happiness, the way we make choices, personal, professional, and political, the way we participate in athletics, the way we understand economic life. In all these ways, we repeatedly appeal to equality, to the balance. Equality is a democratic value we all hold dear in some way. The balance is a symbol of justice and rectitude, of progress and scientific learning, of a life lived well, a symbol emblazoned on our school seal. But in studying these in Galileo, one sees how they transformed our thinking about nature, replacing individual substance, which move closer to their forms as they move in place, quality, and quantity, becoming more fully themselves, with a view of nature that at first glance is equal, prudent, just, and harmonious, but on closer inspection assumes that bodies are always at work against each other in violent opposition. Ptolemy can say the following about his study of astronomy, quote, with regard to virtuous conduct and practical actions and character, this science, above all things, could make men see clearly. From the constancy, order, symmetry, and calm which are associated with the divine, it makes its followers lovers of this divine beauty, accustoming them and reforming their natures, as it were, to a similar spiritual state, end quote. I don't think a physics based on Galileo's de motu could do the same. Galileo sees earthly bodies moving according to principles of tension and opposition. Any rest, order, symmetry, or calm is a tenuous equilibrium that masks underlying tension and opposition. The sorts of causes that are inspired by his study of Archimedes are causes that lead to occasional peace, but more frequently war. Perhaps this explains why Galileo turns away from the discussion of causes in two new sciences, contenting himself with studying what is orderly, symmetrical, and calm, the measurement of the motions. Here he finds the peace he was not able to find when he sought after the causes of the motions of bodies. Thank you.